In today's lesson, we are going to be looking at combinations. So we're just going to do a little bit of a review of what we've looked at in the past in terms of permutations. So at a birthday party, the host has a party favor for each of the 12 guests. And how many ways can the host distribute the favors if A, they're all different, or B, if they have half a dozen of each of two kinds? So basically we have a 6 of one kind and 6 of another. So for A, if they're all different, how many ways can we distribute them? Well, it would just be 12 factorial. 12 different or unique items given out to 12 people. For B, if I have 6 of two different kinds, so let's say 6 of type A and 6 of type B, that means they're identical. So if I were to hand them out or distribute them in a specific order, I wouldn't really notice the difference between the 6 of the one type and the 6 of the other. So in this case, it'd be 12 factorial, but I have to divide by 6 factorial times 6 factorial because I have 6 of type A, let's say type A, and we have 6 of type B, right, or identical favors, so I wouldn't notice the difference. For C, this next one, so again, same scenario, but suppose two guests were allergic to nuts and couldn't have the favors. How many ways can the host distribute if they were all different? So this means then there are only 10 people getting favors. So I have 12 items and I am picking 10 of them, or 12p10, because the two guests are not getting any. So there's only 10 that I have to hand out. Another warm-up. So in Lotto 649, so if you haven't heard of it, it is a Canadian lottery, and it has 49 numbers and is based on selecting 6 of them without replacing them each time. Right? So hence Lotto 649, right? Selecting 6 of the 49 numbers. Now a common question with the lottery is, does order matter? So does the order matter when we're selecting our lottery numbers? Right, or when they select the winning numbers? Well, so let's calculate the number of ways to draw the numbers if order did matter. So we have 49 picking 6, right? 49 letters picking 6. And if we were to do that, we would get 1.0068 times 10 to the power of 10. So a very incredibly large number of possible arrangements. So now think about it. Would having order, or having the order matter, create more or less ways? Basically more or less ways to win. Now consider the probability of winning if order mattered, right? It'd be 1 over 1.0068 times 10 to the power of 10. Right? So that's an incredibly small chance of winning. Would you play the lottery if it was that incredibly small? Would anyone play the lottery if it was that incredibly small? Right? It's not you getting picked out of all those that play, it's you getting the correct numbers. So there's a chance that no one could win. Right? So would you play if this was the case? And you might think, well, no, that's ridiculous. That's too many ways, and you'd be correct. So in the lottery, the order does not matter. It doesn't matter what order you pick your numbers or what order they draw the numbers for the winning prize, because if it was, no one would win, or it'd take an incredibly long time before someone would win, which would make no one would play the lottery. Well, hopefully no one would play the lottery, because if you have a very, 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 very small chance of winning, hopefully you realize that it's not worthwhile or worth your money. So the idea of order not mattering is what we're going to be looking at in this unit. And this is what we call combinations. So a combination is a way of choosing or grouping a set of R objects from a larger set of N objects. So it's very similar to permutations. And if you were to see them, you might not really be able to identify the difference, but that's what we're going to work on. So it's a way of choosing or grouping a set of R objects from a larger set of N objects. So very similar to we're picking a number of R objects from a larger set. Very similar, except we're now saying choosing or grouping. Now it's very similar to permutations, kind of as you hear me talking about this, hopefully you're kind of thinking like, what's the difference? The difference is that order does not matter in a combination. In permutations, everything that we looked at, lining people up, passwords, looking at ways of selecting, pulling something out of a bag, dealing a deck of cards, it all had to do with an order. So order mattered. In combinations, order does not matter. Now, similar notation to permutations, except now instead of a P, we have a C. And it's C equals N comma R, or in the factorial notation, N factorial divided by N minus R factorial, which is the same as permutations, except we have this additional part here. We're also dividing by R factorial. So this is the difference from permutations. And that difference is getting rid of the order, right? So it's just getting rid of the different ways that order could occur, or the different arrangements. So we're implying that order does not matter. It's similar notation or similar definitions. N is just the number of total objects. And R is the number of objects chosen. And we could write it as NCR. This is going to be similar to what you see on your calculator, or in brackets, N over R, not in a fraction, N on the top, R on the bottom. So again, different ways you could write out the combination notation. So let's look at a couple scenarios and see if we can determine whether or not it's a permutation or a combination. So we want to make sure we can kind of identify that. So you have to decide how many ways to put 15 players into 5 different starting positions in a sport. Well, in this way, because we're looking at starting positions, so order will matter in this case, because how you start depends on, again, the order of starting. It will differ if you have 5 different players, right? It's not just if I start first and then we have 4 other people. It's different than if I start last and we have those same 4 people in that grouping. So in this case, this would be a permutation, 15, pick 5, or 360,360 ways. Now, if we wanted to rewrite it so that it used the other method, you might say, okay, how many mini teams of 5? Or if I wanted to make a mini team of 5, right? I have 15 people trying out. I want to make a team of 5. It doesn't matter who gets picked first. They're still on that same team, right? So that's a different way you could word it. B, out of 10 pairs of socks, you have to decide which 3 pairs you want to pack in your suitcase for the weekend. So does it matter which pair of socks you pick first? Does that order differ if you went black, red, green? Is that different from green, red, black? Not when you're packing. Right? The order doesn't matter when you're putting the socks into the suitcase. You're not talking about how you're going to wear them. You're just saying, okay, how many groups of 3 can I make out of 10? So in this case, this would be a combination. 10 choose 3, which which should give you 120 ways. Or if we're using our factorial notation, 10 factorial over 10 minus 3 factorial times 3 factorial, which works out to 10 factorial over 7 factorial times 3 factorial. And again, if you calculate that, you get the same answer, 120. And we'll come back to this notation. We'll look back at that later in a future lesson because there is some kind of patterning with this. C. Out of 30 different songs to listen to, decide how many ways you can make a playlist of 10 songs. It doesn't matter the order the songs are played. So it's kind of clear here. Doesn't matter the order. So in this case, order doesn't matter, right? Maybe I'm going to put it on random, or maybe I don't care. I just want to make a group of 10 songs. So in this case, 30, choose 10, or 30,045,000, 15 different ways. So this one's clear. Order doesn't matter. If I just took that part out, how many different 10 song playlists could I make? Right, that might imply order. Or how many, if I had to rank my top 10 songs, or how many different rankings could I do? Right, or just basically saying order does matter. Something along those lines. So we've kind of looked at a couple of examples. Let's just look at the notation. So in this case, let's just remember the factorial notation is n factorial over n minus r factorial times r factorial. So 10 choose 7, 10 factorial over 10 minus 7 factorial times 7 factorial, or 10 factorial over 3 factorial times 7 factorial, which is 120. The next one, 25 choose 20. Again, 25 is our n, 25 objects, so 25 factorial over 25 minus 20 factorial times 20 factorial, which is 25 factorial over 5 factorial times 20 factorial, or 53,130. Hopefully you're starting to recognize a little bit of a pattern here. And again, we'll come back to this later, but if you recognize the pattern, great. Or kind of how this there's similarities in how some of this works. Look at these two examples. Again, different notation. Again, remember NR for our first. So 8 factorial over 8 minus 3 factorial times 3 factorial, which works out to 8 factorial over 5 factorial times 3 factorial, or 56 ways. 8 choose 3. Same with the second one. For D, same idea. 8 factorial, 8 objects, choosing 5. So we have 8 minus 5 factorial times 5 factorial. 8 factorial over 3 factorial times 5 factorial, which also gives us 56 ways. So there is some similarity between these two. So you get the same, if I'm selecting 5 or grouping 5 items from 8, it's the same as grouping 3 items from 8. So there is kind of that connection between them, and you hopefully should see that in the denominator of this factorial notation. Right? 5 factorial times 3 factorial is the same as 3 factorial times 5 factorial. And we'll come back to this, but again, hopefully you recognize that kind of connection. There are going to be some different scenarios if you're looking at the same total number of items that give you the same answer. So in how many ways can 5 cards be dealt to you from a standard deck? So in this case, in how many ways can it be dealt to you? In this case, order matters. right? Order matters in the way it can be dealt to you. You get one card first, then the second, then the third, and so on. So in this case, this would be the same as saying, well, I have 52 cards, and I'm picking 5 of them, right? Or I'm arranging 5 of them, right? Or 52 times 51 times 50 times 49 times 48, right? Order does matter in this case. Or in this case, and in total, then I would have 311,875,200 ways. Now for B, how many different 5-card hands are there? So now this is different because the 5-card hands is just having 5 cards on you. So in this case, I don't care how it's dealt. Right? I just want to know how many 5-card hands are there. Right? How many different groupings could I have? Now what you could do is you could say, well, I have, in this case, it's going to be, I have 52 cards choosing 5. Because in this case, order does not matter. So 52 choose 5, which works out to 259. So 25, or no, 2,598,960. Now with combinations, you're not going to be using the slot method. It's going to be a little bit different, right? Because the slot method implies that order matters. So in combinations, you're not looking at using the slot method. You have to think about how many options do you have and how many different ways there are to choose them. Now, how many hands contain 5 hearts? So again, talking about hands, order does not matter. So in this case, I have 13 hearts, and I'm going to choose 5 of them. So 13 choose 5. How many hands contain 2 hearts, 2 spades, and 1 club? Now this is a little bit different, right? Because it's saying 2 hearts, 2 spades, and 1 club, again, we're implying it's 2 hearts and 2 spades and 1 club. We see that word "and" in there. That should tell us something, right? That "and," going back to the last 2 units, should tell us that we multiply. So that rule still kind of comes over. We see "and," we multiply. So we look at our hearts. 2 hearts. How many ways can we have 2 hearts? Well, not 12. I have 13 hearts. I'm going to choose 2 of them. Because again, we're talking about hands, so order doesn't matter. So order does not matter. So 13 choose 2 for our hearts. Multiply by 2 spades. 13 spades, choosing 2 of them. Multiplying by 13 clubs, choosing 1 of them. You could rewrite this. If you don't like this notation, you could do 13 2 times 13 2 times 13 1. Just keep in mind it's not a fraction, right? It's just a different way of writing the notation. And this would work out to 79,092 hands. How many hands contain no diamonds? So again, I'm not going to rewrite it again, but hands implies order does not matter. So we're going to be dealing with combinations. So how many hands contain no diamonds? So kind of like the indirect method in a way, we have to think about, well, how many options are there that are not diamonds? So if we take out the diamonds, we have 52 options, taking out 13. So there are 39 total options. So we take out the options, and then we're going to choose 5. So we have 39 options, choosing 5 of them. 57 or 575,575 hands. Next, how many hands contain at least 4 spades? So at least 4 spades, right? At least should imply or, which implies that we add, right? Because at least, we've talked about it before, talks about multiple cases. So if we're talking about at least, it implies or, one case or another, which means we have to add. So at least 4 spades in a 5-card hand, we have 4 spades, or, which means we're going to add 5 spades. So we have our 2 scenarios here. I'm giving myself some room here. So for 4 spades, how many hands of 5 cards could we have with 4 spades? Well, we have 13 spades, choosing, not picking, choosing 4 of them. And we then have 39 remaining cards that aren't spades, choosing 1 of them. So here we have spades. Just choose a smaller font. So it's a little bit of a combination of indirect and the multiplying. So 13 choose 4 times 39 choose 1, plus the other case, which is 13 spades choosing 4 of them, right? Because this is only spades, not choosing 4, sorry, choosing 5, because there's 5 spades in the hand. There's only five cards in the hand anyways, so there's nothing else. If you really wanted to, you could do multiply by 39, choose 0, which doesn't really do anything, doesn't really change it, because there's one way you can choose none of them. So when you multiply by 1, it doesn't really change your answer. So we have our 2 different cases. We're then going to add them up, and we get 29,172 different ways, or different hands. Example 3, there are 12 students on the volleyball team for boys and 10 for girls. And how many ways can a co-ed team of 5 boys and 5 girls be chosen? So a couple key things. And should stand out. And means multiply. We also have 12 boys and 10 girls. So when it's and, we're multiplying. So we're multiplying our 2 parts together, the 5 boys and the 5 girls. So I have 12 boys choosing 5 of them, multiplied by the 10 girls choosing 5 of them, which gives me then 199,584 ways. Right? And again, this is combinations because it doesn't matter what order they get picked in, we're making a team, right? So it doesn't matter what order it is, it's just the group itself. There are 8 girls and 6 boys on student council. How many ways can 4 students be chosen to attend a conference if at least one boy and one girl must attend. Now, you could go through, and if we're looking at 4 students, at least one boy and at least one girl, you could look at different cases. You could also look at the indirect way. So direct, we'll do that way first. So case 1, at least one boy and one girl. So that would be 2 boys and 2 girls. Or we could, and then we would have it as 6 choose 2 times 8 choose 2. That's case 1. We also have case 2, where it's 3 boys and 1 girl. So 6 choose 3 times 8 choose 1. Or we have case 3. 3 girls and 1 boy. So we have, or 1 boy and 3 girls, whichever way you want to have it. So we would have 8 choose 3 times 6 choose 1. And because it could be any one of these cases, it'd be one case or the other. So we would actually be adding these up. So we'd have 420 plus 160 plus 336. And because it's or, we're adding them up, which gives us 916. The indirect way, which also works, so again, the same kind of scenarios apply, right? Direct, indirect. Take your total number of ways without any restrictions. So total ways minus the complement. So minus the complement, or the opposite of at least one boy and one girl. The opposite would be either all boys, or, which means we add, or all girls. So we're subtracting 2 scenarios. So total ways, we have 14 choosing 4. 14 students choosing 4 of them. Minus all boys, which would be 6 choose 4 times 8 choose 0. 4 boys, 0 girls. Plus all girls, 6 choose 0 times 8 choose 4. Oops. So 4 boys, 0 girls. And this is 0 boys, 4 girls. And if you did it the indirect way, you would also get 916. So again, different ways you can think of these scenarios, right? Direct or indirect. Finally, in Lotto 649, 6 numbers are chosen at random from 1 to 49. Right? Again, we talked about Lotto 649 at the beginning. Order does not matter. So you want to keep that in mind. When we're talking about Lotto 649 specifically, order does not matter. So how many ways could you choose your numbers? Well, we have 49 numbers to choose from, and I'm choosing 6 of them. So there are 1, 3, 9, 8, 3, 8, 1, 6. So that means there are, let's rewrite this and make it a little bit easier to read, 13,983,816 ways. Now again, it's ways we can choose our numbers, not ways we can arrange them, because order does not matter. It's ways we can choose them. To win second prize, you must match 5 of 6 numbers. How many second place prizes are possible? So if we only have to match 5 of 6 numbers, that means we have 5 winning numbers. and one losing number. So when we go through this, it doesn't matter what the winning numbers are. There are going to be 6 of them, and we choose 5. So we get 6, choose 5, and, which means we multiply. How many losing numbers are there? Well, there's 43 losing numbers. We choose one of them. So there's going to be 258 ways out of the 14 million ways in total. There are 258 ways that we could win at least second prize, or that we could win second place, or the second place prize. C, we're going to bring combinations or probability into this. What is the probability of winning 3 numbers? So remember, probability is equal to the number of successful outcomes over the total number of outcomes. So the total number of outcomes is I have 49 numbers, choosing 6 of them. So if you remember, total outcomes, and A represents successful outcomes. So in this case, a success is winning 3 numbers. So winning 3 numbers means I have 3 winning numbers. And, because we can't forget that I'm still picking 6 numbers in total, so 3 winning numbers and 3 losing numbers. So I have to still keep in mind, I'm not just looking at the 3 winning numbers, I'm looking at the other losing numbers as well. So I have 6, choose 3, multiplied by 43, choose 3, which gives me, in the end, when we bring this all back together, 246,820 ways to get 3 numbers correct, divided by the 13,983,816. We end up with a 1.7%. So there's a 1.7% chance of winning 3 numbers. Again, you might say, well, that's extremely small. Why am I even going to bother playing the lottery? And you would be correct. That would be a valid reason. You can only imagine, though, if we did this with having to have where the order matters, right? Try doing this again, but order matters, right? So kind of review of the previous unit. What would the percentage be if you had to have the correct 3 winning numbers in the correct order, right? A little bit more difficult because, again, what that order is very specific, increases the total number of outcomes drastically. Right? So again, combinations, order does not matter. A lot of the same concepts from the previous 2 units carry over in terms of looking for and, or multiple cases, or indirect and direct methods of solving. But again, the key thing is that we're using a different notation, the C instead of P, because we're choosing or making groups. We're not arranging. So we want to make sure we can identify the difference. Right? We're not going to combine permutations and combinations, aside from just some scenarios where we have to identify the 2 or the difference between them. But in most cases, the problems you're going to have to solve will be combinations. But it is helpful to know the difference and recognize the difference because, again, we're moving away from the slot method, focusing on combinations.